Now, what is nature of IR spectrum that we are going to discuss? So first of all, we'll try to find out number of bands, absorption bands for the molecules. So there are two types of molecules we consider. One is for linear polyatomic molecules, where more atoms present but the structure is linear, just like carbon dioxide. So for that purpose, you use this formula 3n minus 5. N means number of atoms present in the molecule. So if there are 3 atoms present, you put that value here, you will get value 4 after calculation. So this carbon dioxide will give 4 bands. Okay, if the molecule is not linear, it's having different shape or different geometry, then you are using this formula 3n minus 6 equals to number of IR bands. For example, H2O, which is not linear, which is angular. So there are 3 atoms present in H2O. You put that value here. 3 into 3 minus 6, 3 3s are 9, minus 6 means 3 bands. So for water, you expect 3 bands for different vibrations. For carbon dioxide, you expect 4 bands for vibration, for different types of vibration. There are, 6 type of vibrations. Now, if the molecule is complicated, these are the simple molecules. But if molecule is complicated, just like benzene, which is having 12 atoms. So if you put that value 12 here, 12 3s are 36 minus 6, so 30 bands you expect for the benzene. You can imagine from this, if the molecule having very complicated structure, so there will be hundreds of bands. So you can imagine the complexity, you can imagine the complex nature of IR spectrum. Now, what happens? Although we expect 4, 3 or more number of bands for particular molecule, but this is not the case. Actually, for each vibration, there is not a fixed value, because there are certain factors. We need to consider its stereochemistry, we need to consider its steric hindrance, we need to consider different electronic factors. So the value is not fixed. Along with, there are few other chances, few other possibilities that the overtones, you may get overtones, you may get combined bands. That means those bands which are having nearly same value get combined and we get another band, a new band, or subtraction bands. So if you consider overtones, combined bands, so that from that observations, it is easy to predict that, or easy to say that for each type of absorption, the value where IR absorption is taking place or at which wave number it is taking place, it is not fixed. It is varied from molecule to molecule, but it is always in the range. What is advantage? It is always in the range of wave number, certain range of wave number. So you need not to mug up that values. You have to just remember in what range that particular atom, that particular bond actually giving absorption, IR absorption. So that will help you to decide the structure of the molecule. Now see, for example, I have taken few examples. So remaining all, so lot of examples you can collect from the books or from internet. So due to lack of time and space, I am not able to tell you the value range or the range of wave number for different bonds. So for OH stretching, suppose, that is always occurred in between 3200 to 3600 per centimeter or centimeter inverse. So this is a wave number. So if you get a signal, if you get the absorption in IR spectrum in this region, you can easily predict that the molecule must be having hydroxyl group. That may be of a separate hydroxyl group, that may be of phenol, that may be of alcohol, or that may be of carboxylic acid. What is then? I have taken here another example for CH stretching. That is, this carbon is sp3 hybridized, means all bonds are single bond. You will get, for this bond, you will get absorption in between 2800 to 2900 centimeter inverse, means in that range of wave number. So you just remember that range. For carbon-carbon double bond, that is fixed 600 to 650 little bit here and there, but you remember. But from this information, if your IR spectrum providing that there is a band in between 1600 to 1650, you can easily predict this is because of carbon-carbon double bond. That means your molecule having carbon-carbon double bond. So this kind of structural information you can gather from the IR spectrum. Now I have taken here one more very interesting example. If there is a double bond present on the carbon and you have to just observe band for CH stretching where carbon having double bond. So that ranges from 300 to 3100 3000 to 3100 centimeter inverse. In between that range, if you observe the band, you can easily predict this is because of CH stretching where the carbon having double bond. If there is carbon-carbon triple bond, you will get that absorption band in between this region. If carbon having triple bond, then having hydrogen, you will get around this little bit 50, 100, little bit here and there. But you have to remember, it's a range. If carbonyl group, very popular, if carbonyl group is there, you will get band around 1600 to 1700 or little bit 50 here and there. So you can easily predict that the molecule is having carbonyl group. That may be of aldehydic, that may be of ketonic, that may be of carboxylic group. If you are getting band between 1600 and 1700 centimeter inverse and you are getting OH band in between 3200 and 3600 centimeter inverse, so you can predict the new functional group, that is COOH, should be there. Because of this, you are getting two bands. So in this way, you can gather information regarding the structure of the molecule, and this is what again I am telling you, whatever you are predicting total number of bands, that is not true. That may be more or that may be less because of overtones, combination bands and subtraction bands and many more. Because we have to consider different factors, steric hindrance, electronic factors, even size of the atom, even bond strength. Means bond strength is also actually responsible for the absorption. So we have to consider many factors to predict the structure of the molecule. But in this way, you can go ahead to find out the structure of the molecule or to understand the IR spectroscopy. Thank you.